the posterior, you also have to divide by the evidence. So you will have to, let me first start the recording. Oh, somebody is already recording? That's good. So, by the way, who is recording? Ah, okay, Magnus, super. So when you do a large integral or a Bayesian inference, you have to do integrals. When you want to compute a posterior, you have to divide by the evidence. So technically, you also have to compute an integral then. So computing integrals is really the big, let's say, stumbling block, or can be a stumbling block when doing Bayesian computations. Now, vector graphs by itself do not solve the issue of having an intractable integral. If you have an integral and you cannot solve it because you cannot come up with a closed form solution, that is not what vector graphs will solve. What vector graphs will solve is if you have a large set of variables and the relation, and there's a lot of conditional independencies. So only few of those variables are directly related by conditional probabilities. So if you can write, another way of saying that is that you can write your big model as a factorization, as a product of many small factors, where in each factor you don't have, let's say, all your variables, but only a very small subset. If that is the case, so there's a lot of independencies, let's say, in the graph, right? A lot of arcs or edges that are not drawn. Then vector graphs make the computations very efficient, because there is this basically this inherent mechanisms that there's only computation going on, say, between nodes that are connected, right? You send messages over the edges, and you only send messages so between factors that both have a particular variable in their, let's say, in their argument list. So vector graphs may have, for larger networks, particularly sparse networks, may have a tremendous impact on the computational load. A second big thing of vector graphs is, at least from my viewpoint, is a graphical representation of your model. You can just visualize it. It looks like a flow diagram, and very often that helps a lot. Sometimes graphical models, or let's say probabilistic models, can get very large with lots of equations, or very large models. And then, yeah, if you just look at these equations, it helps a lot to visualize it. So vector graphs have these dual functions: the visualization of your model, and it makes the inference very efficient if you have, let's say, lots of independencies in your model. Yeah, and then we went in this lecture basically through the basics of how to do inference, right? The very basic rule of the sum product rule, also called belief propagation, is how to do exact Bayesian inference. Later on in the class, when we go to variational Bayes, we will also discuss how to do, let's say, approximate Bayesian inference. But for now, it's all just exact Bayesian inference. And you do that with this sum product rule. If you would have a nice palette of nodes that occur a lot, let's say the plus and the Gaussian and the gamma distribution, you can pre-compute these update rules, and then you can make a toolbox with which you can almost automate inference in models that are based off these nodes. And we're doing that. And so that full toolbox is called Fornilab. And I think in this class, towards the end, we do a first, we do some, we have some code with Fornilab. And the interesting thing there is that you propose a model, you write down your model, and then you just tell Fornilab now, compute an inference algorithm. In other words, just schedule all my messages, and then you just execute that. So you don't have to do the inference. The inference is automated by Fornilab. Yeah, that's what I wanted to say. And then with that, I'll let's go to a question and answering session. Let me also just share my screen so that we can maybe point out something in the class. So you can do it. You can go either in the chat or you can just open your microphone and speak up.
Hi.
Hi.
I had a question, but it's more about something in the paper that was recommended to read.
Okay.
I don't know if you mind, but it mentioned that beyond Bayesian vector graph notation, there were also a couple of other notations. Wait. Let me go back up.
Do you want to share your screen? Or shall I put up the paper? Let's see if I will put up the paper here.
Okay, yeah, it's like in the introduction section, and then it's basically right next to where it says introduction, then the text next to it, it says vector graphs are graphical models, blah, blah. In many respects, the different notation systems for graphical models are essentially equivalent.
Yes, yes, yes. So yeah, maybe I should. Let's see if I have another paper by Lulliger here. No, then I'm just going to find one.
I was just interested in what the difference between the notations were, and
yeah, so it's a good question. So here's another paper also by Hans Andreas Lulliger. This is a few years before the 2007 paper, and if I remember correctly, there is so here there is. I'm not sure if you can see my screen. He shows here 4 different graphical ways of displaying the same model, right? So in here A, this is the Voronoi-style vector graph. Now, this is another also a vector graph. In this graph, so it's the same factorization, right? Here's your model P, U, W, X, blah, 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 is P of U times P of W. And B is the same factorization. Each variable is basically a circle here. Each vector, so P of U is a vector, P of W is a vector, is a square node. And then the same idea that you connect your, let's say, your a node to, or you connect your node to your variable if the variable happens to be an argument in your argument list. So this is another notation for the same factorization. You can also do it in, and there's other alternatives. One is called a Bayesian network, the other is called a Markov random field. And they're just different visualizations for sparsity. By sparsity, I mean that not basically that it isn't a fully connected graph. Now, this author, Lulliger, and I agree with Lulliger, prefers the Voronoi-style vector graph, which is A. What is typical about the Voronoi-style vector graph is that the variables are on the edges. In all the other frameworks, the variables are on nodes, you see. So here U is a circled node. I'm not sure if you can see my my pointer, probably not, right?
We can see it.
Okay, so here U is a circle, and here U is a circle, and here U is a circle, but U here in A is on the edge. And so that sort of relates well to the, let's say, the flow diagrams that we do in signal processing and control, right? We have, if you have a background a bit in signal processing control and you draw these flow diagrams, you like to have your operations in the nodes and your variables on the edges. So the Voronoi-style vector graph does that. So it's just let's say, a visualization kind of thing. It's not a big deal. There you can rewrite them in different ways. I mean, the Freudian vector graph and also the other vector graphs have also a formal mathematical description. So you can also formalize mathematically how to convert one graph to another graph. But for the purpose of our class, we just stick to the Forney style vector graph, so to this one. But in the literature, you will also find papers where they use this type of vector graph. They call this a bipartite vector graph because there are two types of nodes. Or the Bayesian network is very popular. But Bayesian networks and vector graphs can also be exchanged. I think personally that the nice thing about vector graphs is that inference is really, you can really see inference, the messages, right? You can see the messages flow over the edges. And this is a bit harder to do in Bayesian networks. So if you're just interested in seeing some kind of a causal structure of how variables are related, then I would say the Bayesian network is a nice one, right? Because it shows here, let's say that y, p of y, or y is a function of x, so p, y, x here, right? And z is a function of x, so p, z, x. So just this causal structure is very nice in the Bayesian network. When you go to inference and you need to actually start passing messages, then I think this graph, this Forney style vector graph, is a nicer graph. But they're both, I mean, it's just a matter of visualization. Does that answer your question?
Yeah, that answers my question.
Oh, okay, super.
Thank you.
Sure. Anybody else? Questions? Or you can put it in the chat. It's true, by the way, that in the exercises, there's only one exercise, and this is an exercise from a previous exam. And yeah, why don't we have more exercises? Partly because just a bit of being squeezed for time, and that's the honest answer. We have been changing the class, making it online, making videos, so a bit of squeeze of time. And secondly, because this is a relatively simple framework. So with one question, I think we basically, the main thing I want you to understand is the sum product rule and how messages flow over a graph. So there isn't a whole lot of variations in the questions. Okay, could you, I see some questions here. Could you explain some more about the derivation of the vector graph of the example given in the lecture? And then I think do you mean this graph? Okay, cool. So we're going to do regression here. And regression is actually something that we do in 2 lectures. So we will revisit this. But basically, I have a data set of observations, x, y, 1, x, n, y, n. And here's a model, right? Here's a model. So y equals some function of x, and what cannot be modeled, or let's say all the errors, f of xi is a prediction for yi, and yeah, sometimes it may not be a right prediction. So we will try to capture that in noise. Here is my full model. I have y of I is w times x. So it's an inner product, linear relation, and there is some noise. We have a prior on the noise, and we have a prior on the W. And now the idea is that by making observations, yi and xi, we want to come up with a posterior for W. Now this can be written in a joint model. What I should have said here, and I've just updated it, but my for some reason it doesn't render yet. I'm not sure, but this should be P of dw comma epsilon, right? And by D I mean X and Y, but W is W, and then comma epsilon. That's the joint model. And the joint model breaks down into a prior, P of the data given W given epsilon times P epsilon. You can kind of see that this is a correct factorization of this joint model. And here I basically specify that further by saying, yeah, this prior, I just take it from here, right? This is a Gaussian. This is another way of what I mean. If my noise is given, if W is given, and if Xi is given, then it's the prediction of let's say yi is just a deterministic relationship, right? If I mean yi equals w times xi plus ei, so I can also say yi minus wxi plus minus ei equals 0, right? And this delta says that it's basically a probability distribution on what's in here, and this is only, let's say, it's only unequal to 0 if this expression equals 0. And so this implements a deterministic relationship. Using delta functions is just a way of, let's say, implementing deterministic relationships through a probability distribution. And here, this is the prior for EI epsilon. I just take it from here. This thing in the middle is just my my top equation here. The middle equation is this one, and the bottom equation is this one. So now I need to make a vector graph. So what I see is, so then I drew this vector graph. The way I usually do this is go over it in a generative direction. I say, okay, if I have W here, W is, here's an equality node. So this is W, but this is also W, and this is also W. If I have W and I do a dot product with X, then I get something. And if I add epsilon, then I get Y. And what do I know about epsilon? Well, I have a prior of a Gaussian prior, and it has a parameter theta square. Is that all we know about W? No, we also have a prior. So I connect here a prior, and I connect that with an equality node. I wouldn't absolutely need the equality node because I have, but I want to send out a message out of this equality node to the right. So that's why I'm using an equality node. But I hope you can see the little graph is consistent with this model here. This node NW is this one. Sorry, the n of the Gaussian over EI is basically what's going on here. And everything here is the linear regression thing. For some reason, I keep getting muted without actually pressing a button. But okay, so now we need to, we want to get the message to. Are you still, can you still hear me, by the way? Okay, so now we need to come up with a message I get muted for some reason. Well, basically what we do then is we pull up the graph from here, from W, and then we start passing messages from the terminals towards the root. This is then the root. So this message, messages like here, and messages like this. The square nodes mean, the square black nodes mean I know the values. I just plug in the values, right? I have assumed here that I know sigma squared, so I plug in the value. XY and YY are observed. So I can plug in values here. So that means, by the way, that there is a delta message going here from Y, and there's a delta message here going from X. And there's a delta message here. And yeah, I just pass the messages, and I do the sum product rule, and then, okay. So you say that makes it much more clear. Thanks. Good. Then I'll stop repeating myself. But yeah, that's the idea. So one way of looking at it is that, and I usually draw them this way, that the prior here comes from the left, and message 7 is the likelihood. If I draw a big box around here, right, everything here below here, and the outgoing message, and so I would do the closing the box rule, then I would integrate out over X and over epsilon and over Y and integrate. So it's a function of W. But the data is included. It's actually the likelihood. And so you have a likelihood message and a prior message, and this equality node will just fuse the two, will just multiply. A will just multiply these two, and that's your posterior. And yeah, so now you can imagine that you can see message 8 as a new prior and do the same thing for X2 and Y2, and then come up with a posterior after 2 observations and consider that a new prior, and so forth. You could have another scheme. This doesn't have to be. You could have made, let's say, started from here. 1, 2, 3, 4, 5, 6, 7, 8 would also be fine. As long as you start from, let's say, from the terminals, right? And I could have said that going out from X equals 1, and this is 2, and this is 3, 4, 5, 6, 7, 8 would also be fine. Why is the symbol equality used for multiplication? Okay, so it's not a multiplication node. Here we do multiplication. This node, and we've talked about that here at top. Yeah, they're basically branching points, right? What this node does, you use this node if you have a factorization and you have 3, and let's say an X2 appears in 3 factors. Here X2, X2, X2. Well, we say that a variable is associated with an edge, but an edge has only 2 sides. So that's not possible. So what we do is we just add some auxiliary variables, and we connect this. But what we do is the function in this node is delta x2 minus x2 prime and delta x2 minus x2 double prime. The effect is that the beliefs over x2, x2 prime, and x2 double prime are always the same. So I have extra variables, but since this constrains that the posterior beliefs over these variables are the same. Now, in order to compute the outgoing message of this equality node, we just have to do the sum product rule, and I'll do it for you. It's in the optional slide. I wanted to keep the so there's an optional slide here. So here's the equality node. So So there's three variables, x, y, z, right? And this is the factor, z delta of z minus x, delta z minus y. And then let's say I have an incoming message here over y, and I call that mu forward y, and an incoming message from x, mu forward, both towards the node, and I want to compute this outgoing message. So the sum product rule says, well, you have to multiply the incoming messages, so mu x, mu y, times the factor, which is this, delta z minus x, delta z minus y, and integrate out all the incoming integrate over the incoming variables, x and y. So this is the sum product rule. Now, if I do that, and you can just see that yourself, because you have these deltas, you can basically substitute for x, you can substitute z, and for y, you substitute z. So this is what you get. You get the outgoing message function of z message, but now you plug in z, and the second incoming message times the second incoming message, and you plug in z. So you can multiply the two messages. It's the fact that I multiply is not because I put a multiplication in here. I actually put this node function in here. The reason why I multiply is because the sum product rule evaluates to a multiplication. And so you can interpret that as usually one of the incoming messages is a prior and one is a posterior, is a likelihood. And then the output, yeah, you have to multiply them, and that becomes then your posterior. Just like what happened here. Just like what happened here. Here's your prior, whatever, message 7 is your likelihood, and message 8 is the posterior. So we multiply here because that's what the sum product rule says. Let's see if I can. There's another question here. I was wondering why a configuration is only valid if FW unequals 0. Yeah. Look, this go all the way to the top here. So these graphs, they represent. So here's a factor graph, right? And so it's a function of x1 through x5. These are usually, they represent probability distributions, and these are just, you know, other probability distributions or smaller probability distributions. Basically we say, well, any set of values for the variables that makes this probability distribution unequal to 0. Okay, so that's, let's say that's valid. We don't want to have a combination of let's say of variable values that basically makes the probability 0. That cannot occur, right? That cannot. That's not valid because it cannot occur. I cannot observe values for my variables for which the probability equals 0. All right, so that's sort of the idea. Let's see. I don't see any other question, but I'll leave it to you to add a question or to open your microphone and just speak up. So if not, then basically, well, that was then the factor graphs. So factor graphs are very interesting, I think, particularly for large models. So the next class is going to be about basically about Gaussians, how to compute everything when you have a Gaussian. It turns out that if you use Gaussian distributions, then you and you are in a linear system, then everything remains Gaussian. In the same way that if you have a sinusoidal signal in a linear system, it remains a sine wave, right, with the same frequency. And you can say similar things about, let's say, a variable that we describe by a Gaussian distribution. If you pass that through a linear system, so you multiply it by constants and you add other Gaussians and so forth, you will always have Gaussians throughout the network. And so we're going to compute with that a little bit. Ultimately, with that little, let's say, that the fact that it remains Gaussian it means that you can analytically compute something that's called a Kalman filter. And I think I'm not so sure, but I think we actually touch upon the Kalman filter already in the next class. But it's basically a review of all the beautiful things you can do with Gaussian distributions. And yeah, that's it. So one more question. How would we expect this lecture on vector graphs to be included in the exam? There are not many questions for us to prepare ourselves, so that's why I ask. Yeah, so I may add another exercise, but the exercise, let's say, that's currently in the exercise is very representative in the sense that I could ask you to compute, let's say, a simple work out a simple sum product rule. I could ask you if I have a model, draw the vector graph, and I could ask you how would the messages flow. As we talked about, very likely it's going to be multiple choice. So you're going to have 3 or 4 answers, and you have to pick one of them that that you think is the right one. So something like that. Yeah, and then as Wouter says, we will be working with vector graphs in the probabilistic programming sessions. So you'll get enough practice with vector graphs.
I have a question, please.
Yes.
Under the section of inference by closing boxes, there is a demonstrating example. Actually, I couldn't figure out how f of x3 is given in form of product of some factors a, b, c, etc. Okay. The equations above the upper figure. Yeah, these 2 equations.
You mean this equation?
No, the first 2 equations.
This.
Yeah.
Oh, yeah. So, if this is I just state that this is the case, right? I mean, and this is true if this is a probability distribution. If f is a probability distribution, and so then this is the joint probability distribution over x1, x2 through x7. And if I now sum out over all values for x1, x2, x4, 5, 6, 7, then what's left over, and that's just the rule of the sum rule, right, or the marginalization rule. What's left over is the probability for x3. So here I just put it in a more general way, and I say, yeah, this is just marginalization, really.
Yes,
now,
I mean, the product factors, f of fa of x1, fb of x2. How did we found these from the joint probability?
Yeah, so that's yeah. So this is just I just declare that, right? I just say, I mean, maybe I should have phrased it differently. I say, I should have said maybe let f of x1 through x7 be given by this factorization, right? If f is given by this factorization, then this sum, well, becomes the sum on the second row.
Okay.
And then once we have a factorization, we can draw the graph. And that's this, right? Because the vector graph only basically reflects the factorization in the model. Maybe it's a bit unfortunate in my formulation, but maybe I should have said, maybe I'll update that. Let f be given by this factorization, and assume we wish to compute the marginal f bar f3, which is given, which is defined by this sum. Then we can plug in, of course, the factorization, we can draw a graph, and then we can do this basically this message passing, going from terminals here, starting in FA and then FB, and basically moving all the messages towards X3.
Okay, my second question is about the figure. We have drawn directed graph, although it was mentioned in the text above that the Forney factor graphs are undirected graphs.
Yeah.
And I don't know how these directions are drawn like this. What's the assumption?
So it is an undirected graph in this in the sense that the arrow that I draw here has no computational meaning. I mean, if I the arrow of let's say of the edge is only meant. So because I'm going to have two messages on each edge. I'm going to have a message, let's say for X3, a message going from FE to FC, and I'm going to have a message from FC to FE. Now I need to come up with a notation. Now what I can do is say, okay, this message, let's say from FC to FE, I can call that mu and then underscore C arrow E or something like that. And some people do it that way. And then this message from FE to FC would be mu underscore E and then arrow C. Or what you can do is you can add an arrow, and then you call this, the red one, the forward message, which is in the direction of the arrow, and the blue one you call the backward message. And that's what most people do. So most people, but not, I mean, not necessarily this way, but we just add these arrows, and then we can call our two messages, we can distinguish between them by saying there's a forward and a backward message over X3. And we write that by the backward arrow and a forward arrow. And how is forward defined? Well, relative to the arrow of the edge. But it's just so it's a notational thing. I could have drawn, let's say, this arrow on this side where towards FC, and then the red one I would have called the backward message, and the blue one I would have called the forward message. And aside from that, everything would be the same. So it's an arbitrary notation, if you will, but it's a notation to distinguish between these two messages that flow over an edge.
Okay, thank you. That's clear.
Okay. Do you really need an arrow in the edge? Only having the blue and red arrows would also suffice. The blue and red. You mean for the if you mean that I only have forward and backward messages for X3, that's true. But sometimes I need marginals for other variables as well. Let's say for if I need it for all of them, then I need to pass messages basically through basically from forward through the graph and backward through the graph, and I would get messages on each edge in both directions. On if I'm margin 3, interested in, let's say, the others as well. In many models, I just want to compute, let's say, the information in the graph for all my hidden variables. We'll talk about hidden variables later, but yeah, so it's just, in this case, it's only for X3, but generally it could be for the others as well. Yes. I mean, what I mean to say is that you can the fact that the arrow is in this direction by itself doesn't have a computational implication. It's a notational thing. I haven't really followed the chat fully because I was babbling away, but did we get answers to the questions? Is the arrow of mu x7 wrongly directed? Mu x7. Yeah, good one. That's the wrong direction. Very good. Yeah, so this, damn, now I have to update my graph. Okay. Yeah, I'm going to update that. This is a backward, this little arrow above the mu should be a backward arrow. Good one. Okay, so then if I don't see anything anymore in the chat, but feel free to type something, but I don't see anybody typing, and I don't hear anything. So then I'm just going to close the session, and I'm going to fix my error here, and I'll rephrase this formulation a bit so it's clear that it's per definition this way. And then good luck with studying the Gaussian lecture, and then I'll see you on Friday. Bye-bye.